Okay. So last time we talked about graphical matroids, and we saw how you can use minors to talk about graphical matroids. And I stated this theorem that a matroid is graphical if and only if it doesn't get obstructed by one of 5 things. There's 5 matroids that can live inside a matroid to stop it from being graphical, and that's the only thing that can go wrong. And we said that that was a consequence of the fact that graphical matroids were closed under minors. Okay? That's what allowed us to do this. Now, linear matroids are also closed under minors, and so today I want to talk about that question.
Can I ask you just one question about the thing we did last time?
Yeah, sure.
So, this is an if and only if. So, if one of those guys isn't in there, but figuring out that one isn't in there isn't necessarily so.
That's very true. So, last time I said a matroid is graphical if and only if it doesn't have one of these 5 matrices inside it. Now, how do you tell? Well, it's still a serious problem, right? If I give you a huge matroid, how do you go around looking for the minor that you're looking for? Well, it's not clear, but at least, I mean, it makes it a little bit simpler, but this is still an algorithmic question, and honestly, I don't know how hard it is. There might be easy algorithms, there might not be. I'm not sure, honestly. But it's something that we can definitely look into if you guys are interested. What about linearity? Well, here again we're going to use the fact that any minor of a matroid any minor of a linear matroid is linear. Okay. Now, I want to strengthen this a little bit and say that any minor of a... What I want to say is that this statement is also true if you fix the field where you want to represent your vectors, your matroid. So any minor of a matroid representable over some field F is also representable over that field. And remember that being representable over a field F means that you can, this means that you can make your vector configuration live in some vector space over the field F. Okay? So why is this? Because, deletion means deleting a vector. That doesn't depend on the field that you live in, right? That doesn't, you can do that over any field. And the projection you can also do over any field with a little bit of care. But basically, the 2 constructions that we showed for minors work over any field. And so now the question that people ask themselves is, when is a matroid linear? But somehow people never seem to be asking this very question. What they tend to ask is, when is a matroid representable over a given field? These are two separate questions. Okay? And somehow this is the one that people in... This is somehow the mainstream question in matrix theory. This is the one that they ask themselves. And actually, I spent the last 2 days looking in the literature, and I can't find the answer to this question, actually. And I want to look into this and see why it is. I mean, my suspicion is that this question is too difficult, and that's why they ask this one.
Yeah, the second one seems like a much more reasonable thing to try to answer.
It does. But still, I couldn't find in the literature concrete results that show why this is difficult. So the point is that if a matrix is representable over some field, then it's linear. Okay. So here you're allowing yourself to represent over any field, and here you're allowing to represent over a given field. You know, the field of 2 elements, or the real numbers, or whatever.
So that's why if it's linear means you have to somehow check all fields.
So you have to find the field.
Right. So the question of being linear means it's a question about any possible field. So I want to put here that I think this is too hard, but honestly, I mean, I thought this was going to appear as the first comment in any matrix theory book, and I've looked in several, and I can't find the comment that says why this is hard, and I'll keep looking, and I'll let you know when I find it, and if you want to also help me look in the literature, that would be great. The point is that this is the question that people know a lot about, okay? And so, for example, we showed last time that the Fano matroid is representable only in characteristic 2.
And there must be some people who have shown that certain matroids can't be represented over any field.
Right, so we'll see examples of matrices that are not linear. Okay? And I should say, actually, this is not a trivial question, and someone in Bogota posted this conjecture on the board, on the forum, that any matrix was linear. And so far, we have no evidence against that conjecture. But today, for the first time, we're going to see a matrix that is not linear. And it's not easy to construct it, actually, but we'll see it. Last time, we saw the first hint that things might not be linear. You know? The Fano matrix we saw can only be linear over characteristic 2. Okay? And let me just give you a summary of what people know about this question. So, representable over the field of 2 elements. People understand this. So the restricted minors, the forbidden minors. It turns out there's only one, which is the uniform matroid on 4 elements of rank 2. So this matroid is not representable over the field with 2 elements 0 and 1. And any matroid that is not representable over this field contains this guy as a minor. This is a nice theorem, and it says really that geometry over this field is somehow described combinatorially just by this minor. This is the forbidden minor. This is a theorem of Todd from 58. Okay. So people like this theorem a lot. And then the next thing was this. Well, so the next field is the field of 3 elements, 0, 1, and 2, where 2 times 2 is 1, etc. The field of 3 elements. So here people realized that these matrices were not representable. These 2 uniform matrices And we saw last time that the final matroid and its dual are not representable over this field because it doesn't have characteristic 2. And this field 2 is not equal to 0. But people didn't really know that this was the complete list, but they suspected it for a long time, that these were the only forbidden minors. And then there was this kind of ambitious conjecture that actually, if you look at any field, any finite field, there's a conjecture that this is a finite list.
Is it a finite field or a finite characteristic?
This is the final field.
Just the
I
plane field of order.
the plano, yeah. So here Q is supposed to be a power of a prime, and I don't want to go into this too much in case some people are not familiar with the finite fields. But anyways, so the point is that finite fields look like this, and there was a conjecture of Rhoda. And this conjecture is from 71, saying that actually you could characterize matroids over any finite field by a finite set of forbidden minors. This is not clear, and in fact it's still a conjecture, still open. So there you go, that's the final project for you guys. Still open. Okay. And people had these for a long time, and they couldn't figure out if that was a complete list or not, and then finally they figured out that it is. Bixby and Seymour separately proved this in 79. Okay. And then they said, okay, let's push it one step further, you know. So a field of 4 elements, okay. And then they found that there was a list of, actually this is a conjecture in Oxley's book. There's a list of 6 matrices. 1, 2, 3, 4, 5, 6. And it's a conjecture in Oxley's book that this is it. These are the only ones. And actually, this is one of the big things that people are very happy about in matrix theory recently, is that they found out that this conjecture is false, but actually it's almost true. It's just that they missed one matroid. So there's 7 matroids, 7 obstructions, and that's it. And this is a result from 2000 by Gielen, Gerards, Kapoor. Okay. And again, you can imagine this is one of these proofs where the first thing you have to do is show that these 7 guys are not representable over GF4, and that's already work. But then the difficult part is the opposite, which is you start with a matroid that is not representable over this GF4, and you somehow have to, in your proof, split it into 7 cases, and each one of these 7 cases leads to one of these 7 obstructions. This is hard. This is hard. These are hard theorems, and this is why it took so long to do this. And so, of course, then you can continue. Okay, the field of 5 elements, but actually, what these guys say is that they don't think that this conjecture is true, and they think that they really got to the end of it, and so they think that for 5 elements, mathematicians are very scared of making conjectures and then being wrong, so they say that they fear that this conjecture is not true. This is what this paper says. And the reason is that there's a real difference between GF4 and GF5 that people do understand now, which is that if you have a matroid representable over GF4, then there's only a small number of different linear representations. I forget exactly what the result is, but it's something like if you have a matroid over GF4 and it's representable, then there's only like 3 ways of representing it. But in GF5, people have found matroids that are representable and that I have arbitrarily many representations. And this is why they really think that this is different from this. And they use what I just told you to prove GF4. at least their technique is not going to work for GF5, and that's why they think GF5 is false, because how could their technique not work? But really, it seems like there's a qualitative difference in this jump. And I don't know, honestly. I don't know, but we might say a little bit more about this, about different representations of the same matrix. But I honestly haven't. I'm not familiar with this result, and I don't know the reason why GF5 is so special. Why GF5 becomes very difficult. Okay, what about? So there's two things that I think are. I mean, here, there's 2 points of view that you can take. So one point of view is who cares about these fields? We never care about these fields. And some people take this point of view, that these are maybe not so interesting. I mean, so it's interesting that these things are characterized combinatorially, but what I care about is the reals, maybe. That's my kind of vector space, What about the reals? Well, I'll tell you why. The thing is, people understand the reals, and actually, for the reals, this list is not finite. Infinite list. It might worry you a bit, but it's in your homework 5. I mean, I'll show you how to do it. And I'll show you the. I mean, what you have to do basically is find infinitely many matrices that are not representable over R, and that are not minors to each other. And I'll tell you which ones those are, and you just have to prove that. It's a reasonable question, don't worry. And so this is why people think this is more interesting, because well, here the answer is nice, and here the answer is not nice. Okay? The answer is that the geometry over the reals is too complicated to characterize it by excluded minors. Okay? Now, there is an interesting result, which is what if you want to understand the matrices that are representable over any field? Any field.
Every field.
Over every field. Every field, right. I think this result is very interesting, and so this is understood, and the only obstructions are U24, the Fano matroid, and its dual. Why does it not make sense?
So maybe we have the same question. So my question came up earlier, which is the thing we were showing the other day about U24 being the minor of U35.
U25 and U35. So I think the reason this is not making sense to you is because, for example, U35 is not on this list. But U24 is a minor of U35. That's why it's not on that list. So we know that U35 is not representable over every field, but the reason is that U24 is inside it.
But is that saying that if I find in a matrix, if I find U24, but I don't find U25 or U35, then it is representable over GF3?
Over GF3. Okay. I really feel like if this question really is not true, I mean, if this conjecture really is not true, Rota's conjecture, this is going to be one of these things where you see the proof and people are going to be like, it's obvious. How didn't we think of this? And really, I do think that this could possibly be a reasonable question to think about. It's not easy, but I really think it's going to be one of these things where maybe people were trying to prove that it was true, but to prove that it's false, you just have to kind of produce an example. I don't know.
Well, then, if you just produce an example, though,
I mean, of course, the questions you can ask here never end, and people make a living out of asking these kinds of questions. And you know, some people think it's great. Some people think other parts of matrix theory are more interesting. It's up to you guys what you think is interesting. If you want to think about this more, this is definitely a good place to look for a project. Now, there's another open question that I think it's kind of shocking that it's open, which is what is the easiest matroid that we've seen? The uniform matroid. And the question is, where can you represent the uniform matroid? Over which fields? This question is wide open. I mean, there's some progress. For example, for U2N this is known, and it's also in your homework. You're going to describe exactly where the matroid U2N can be represented, but for bigger values of R, there's some progress, but people don't know. Which shows that this question is hard. I mean, this question of representing over a specific field is a difficult question. But so far, we still haven't seen a nonlinear matroid. Okay? We've seen matrices that are not representable over GF2, over GF3, but we haven't seen a matroid that cannot at all be represented as vectors. Okay? And I'm about to, well, let me show you another matroid. Okay? So another matroid that we don't know yet. So last time we met a new matroid, which was the Fano matroid, and our new friend is the non-Fano matroid. The non-Fano matroid looks like this, just like the Fano matroid, except that it doesn't have this loop around. That's the non-Fano matroid. So the circuits are 1, 2, 3. Well, 3, 4, 5, 1, 4, 7, etc. So we said that if you see 3 guys on a line here, then that's a circuit, and any 4 are a circuit. I mean, any 4 are dependent. And so any four guys are dependent here. So for example, 1, 2, 4, 5 are dependent because this is supposed to be a rank 3 matroid. So because I drew it and it's in the plane, it's in rank 3. And what's a basis? A basis is 3 guys that are not on a line, like 1, 2, 4. Okay.
And there are no sets of 3 guys that are not on a line. There are no sets of 4 guys.
The 1, 2, 4, 5 is dependent. So that's a circuit. Or 2, 3, 4, 6. Any 4 guys are dependent. So basically the basis of these matroids, are the sets of 3 points that are not on the line. Okay. Another way that you might want to think about this is, and I'll say about this more in a little bit, but you can think of this as really a point configuration in the projective plane. So each one of these points is a point. Each one of these lines is really a line, and so these 3 points are on a line, etc. And a basis is 3 guys that are affinely independent. I'll say a little bit more about that in a second. But in other words, the dependent things are any 3 on a line and any 4 are dependent. to be, for example, 1, 2, 3, 4 is not a circuit because it contains 1, 2, 3. So in fact, I should just say any 4 which are minimal, yeah, any 4 such that no 3 are unaligned.
So basically, those lines are giving the sets of 3 elements that are not bases. Every other set of 3 is bases.
Right. So every line represents 3 guys that are not a basis, and any other triple like 1, 2, 7 is a basis. And you have to check that this is a matroid by checking the basis axiom or checking the circuit axiom, or by giving a representation. And a representation of this is this one: 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1. And 1, 1, 1. For example, these 3 guys are dependent because 1, 0, 0 plus 0, 1, 1 is 1, 1, 1. So on.
Well, that's, I don't have a family, but last time it was that circle that's not there anymore.
So last time I drew this picture and I said this was the Fano matroid in F2. But if you consider this configuration over the reals,
Now it works, but it doesn't have that extra circuit.
over the reals or over anything, where 2 is not equal to 0, then these 3 guys are independent. So this is the non-Fano matroid, and what I want to show is that the non-Fano matroid is not representable over fields of characteristic 2. Okay. Or let me just say it's not representable over. Yeah, exactly.
But it's hard to prove. You need this S&A representation. You have to show that you can't have another representation.
So I'm going to show it over GF2, and I'll leave it to you to check that this also holds for any other fields of characteristic 2. I'll show you how to do it in GF2, but it's not too different. Okay, suppose it is. Suppose I represented it over GF2. So now these guys are vectors in GF2 to the 3. Now, again, even though this is a finite vector space, I can still do linear algebra. And because of linear algebra, I can assume that 1, 3, and 5 are my standard basis vectors. If they're not, I just do a linear transformation that sends them there. So vector 1 is 1, 0, 0. Vector 3 is 0, 1, 0. Vector 5 is 0, 0, 1. It's kind of a bad notation to have called these 1, 2, 3. Let me give them letters. A, B, C, D, E, F, G. Okay. So this is A, this is C, this is E. Now what can you tell me about B? Well, you see, B is a linear combination of A and C. Okay? But what are my scalars in GF2? My scalars are 0 or 1. So what are the possible combinations of A and C? I have 4 combinations. 0, A plus 0, C. But B is not equal to 0 because it's not a loop. The 4 combinations of A and C are 0, A, C, or A plus C. But B is not 0 because it's not a loop. B is not A because A and B are independent. B is not C because B and C are independent. So the only thing B can be is A plus C. One, 1, 0. And in the same way, D has to be equal to C plus E, which is 0, 1, 1. And F has to be A plus E, which is 1, 0, 1. So therefore, B plus D plus F is equal to 2, 2, 2, 0, 0, 0. So therefore, B, D, and F are dependent. And that contradicts that in this matrix, B, D, and F are not dependent.
How is that any different over any other characteristics? Or you might have
That I have other linear combinations here, but the proof works in the same way, but with a little bit more care because I have more scalars in my field. Okay. The non-final matrix is not representable over GF2 or any field of characteristic 2. Okay. Theorem. This matrix is not linear. The direct sum of these two guys.
Careful.
So this is a direct sum, okay? But I can also just represent it as this point configuration. This matrix is not linear. This is kind of a cheap construction, I think, but it's, anyway, we really want to see a nonlinear matrix, and this is the easiest example. Suppose it is. Suppose we represent it over some field F. Okay? That means that I represented this guy over F, right? Because this guy is a minor. So I represented this guy over F, and that means that the characteristic of F, by what I just showed, has to be different from 2. But now I restrict to this guy, which is also a minor, and I also managed to represent it over F. But in the last class I showed that this guy was not representable except for characteristic 2. Done. Okay. There's my first nonlinear matrix. It's kind of cheap, no? But, I mean, it's a proof. It's a proof, so this matrix is not linear. Okay? So that's good to know. There are nonlinear matrices, but now I'm going to show you some nonlinear matrices that are more interesting. And to do that, I want to elaborate on what these pictures actually mean. The point that I want to make is that if you are, for example, in, say this is R2. Okay, and you take some point configuration here. There it is. I want to claim that this actually defines a matroid by saying that, for example, these guys are on a line, and so they are dependent. These guys are on a line, so they're dependent. These are dependent. These are dependent. These are dependent. And any 4 are dependent. And I claim that that's a matroid. Let me do that in general. So let's say that you take a bunch of points and you say that they are affinely dependent. If there exists a combination such that, so A1, B1 up to AN, VN is equal to 0. So their combination is 0. And the scalars that you used add up to 0. Okay. It is 0. And for example, let's see it here. So here's A, here's B, and here's C. What is the linear combination between A, B, and C? Well, B is the midpoint of A and C. So vector B is equal to A plus C over 2, which I write as minus A minus 1/2 A plus B minus 1/2 C is equal to 0. So I have minus 1/2 plus 1 minus 1/2 is 0. And so this notion of affine dependence really says you're not allowed to have 2 points on a line, you're not allowed to have 3 points on a plane, etc.
But you also want all the AIs not 0.
And I want to say that that at least one of them is not 0. No, in other words, I have no 3 on a line, no 3 points on a line, no 4 points on a plane,
No 3 points on the line.
there are no 3 points on a line, so you're never going to see this.
When? If you have a set that's affinely independent.
Affinely dependent. Right. In other words, affinely dependent if you have.
You're affinely independent if you have 3 points on a line. You have 3 points.
If you are affinely dependent, it's because you have either 3 points on a line or you have 4 points on a plane, like this, or etc. 5 points on a 3-dimensional space, so on. I left a space here because I want to also say 2 points on a point. If you have 2 points that coincide, then they are dependent. Okay? So, proposition, this defines a matroid. Of this configuration, this point configuration. Okay. And this is easy. You can just repeat the proof of linear independence, and it works exactly in the same way. Or you can show this proposition: a loopless matroid is linear if and only if it's one of these guys. So if you prove this theorem, then the affine matroid of a point configuration is a linear matroid, and therefore it's linear. Okay? And this is easy, actually. This is let me first give you the proof, and then I'll show you the geometric picture behind it. The proof is very easy. The proof says, let's suppose that you have these guys and you have an affine dependence. Okay, so you have these points and you have an affine dependence. Now what I'm going to do is construct a linear matroid. What I'm going to do is I'm going to consider each one of these vectors with a 1 preceding it. So these are vectors in one more coordinate. And I claim that this affine dependence turns into a linear dependence here. Why? Because if you take a1 times 1 comma v1 plus an times 1 comma vn, then in the first coordinate you're going to get a1 plus dot 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 plus an, and then in the remaining d coordinates you get a1 v1 plus dot 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 plus an vn. And this first coordinate is 0 because these guys add up to 0, and these d coordinates are 0 because this linear combination is 0. So it's 0. So what this shows is that if you have some point configuration, then by sticking ones ahead of these vectors, you get a vector configuration such that affine dependences here turn into linear dependences here. Okay. To go backwards, what you do is you take any linear matroid, which is given by some vector configuration, and all you have to pull off is that the first coordinate of all these vectors is equal to 1. I mean, so in other words, what I showed so far is that if I have an affine matroid, it's linear. Okay. And for the other one, you take a vector configuration, so let's say this is f d plus 1, and you take some vector configuration here. Okay. How do you make an affine configuration out of this? Well, this gives you a hint of what to do. You just consider the plane where the first coordinate is equal to 1. So some hyperplane here. And each one of these vectors is going to determine an intersection point here. Okay. Now, we know that if we have a vector configuration, we can scale the vectors, and that doesn't change the linear dependencies. Okay. So the linear matroid determined by these vectors is the same as the linear matroid determined by the vectors that go up to this plane. And now we're in this situation where if you get rid of the first coordinate, you get your affine configuration, which is why we need it to be loopless. Because the one thing that you lose is the loops. Now, if they point this way, then the intersection is this one.
It's a scalar.
And it is just a scale, except that you scaled by a negative scalar. What if you have a vector that is where x1 is equal to 0? Then what you're going to do is take your vectors and apply a linear transformation that rotates them so that nothing is parallel. And if you rotate, that doesn't change the linear dependencies. And now you don't have anything parallel, anything on the head. In an example, and what I want to illustrate to you now is that I've really made my job more difficult by drawing this example that I keep drawing. 1, 2, 3, 4, 5, 6. I keep drawing this example of vectors, but I could be much more economical by just intersecting with a plane, which is what I did here. I just take my vector configuration and I slice it through with a plane. So instead of drawing this configuration, what I could have done is just slice through with a plane. Okay? And the plane is maybe this one over here. And now vector 1 becomes this point, vector 2 becomes this point, vector 3 becomes this point, vector 4 becomes this point, vector 5 becomes this point, and vector 6 disappears. And now what I have is a configuration in the plane that looks like this. 2, here I have two guys that are living side by side, 4 and 5. Here's 3. Here's 1. Okay. And people like to denote loops, so I lost my loop, but if you want to keep track of loops, then people just put an empty circle that means loop. So 6 is a loop. And so this is how people would conventionally draw this. Okay. So this is a picture that's easier to draw, and when you get used to it, actually you're gonna get used to reading this picture better than this one. So for example, what are the circuits? How do you read the circuits from this picture? Well, there they are, right? 3 points on a line, 2, 3, 4. 3 points on a line, 2, 3, 5. 2, 3, 5. Oh. Here you have 2 points on a point, 4, 5. Anything else? 6 is my loop. Anything else? How about, so I took care of 2 points on a point. I took care of 3 points on a line. What about 4 points on a plane? Like 1, 2, 3, 4. Do I need to put that? Well, I don't need to put 1, 2, 3, 4 because 2, 3, 4 is already a circuit. Okay. If you look at any 4 points on this plane, you're going to see that 3 of them are on this line, and the other one is 1 maybe. So these are my circuits, and this is how you read these pictures. And after a while, you'll get used to this, and you'll hate me when I draw vectors because now you can look at a 2-dimensional picture instead of a 3-dimensional picture. Okay, and there's a very practical reason why this is good for us, which is that we know a lot about the geometry of the plane. Now, we may know a lot. The question is whether we remember a lot. But all of you have taken courses in plane geometry, starting maybe in high school. And there's some theorems in plane geometry that you may or may not remember. So, for example, there's a theorem that looks like this. Suppose you have 3 points on a line, 3 points on a line, and you draw these x's here. X, X, X. Label these points 1, 2, 3, 4, 5, 6, 7, 8, 9. Does this look familiar? So there's a theorem in plane geometry that says that 7, 8, 9 are in a line. It's called Pappus theorem. 7, 8, 9 are on a line for any projective configuration, for any point configuration in the projective plane like this. Okay? So, what is my nonlinear matroid? It's this one. I just drew a nonlinear matroid for you. What are the circuits? Well, the circuits are these, Circuits are all the things that you know how to read from that picture. 1, 2, 3, 4, 5, 6. Right. 2, 6, 9. Yeah, I'll say that in a second. For example, 2, 3, 8, 9. The circuits are the 3 points on a line, the 4 points on a plane. Okay. But the point is that this line is missing. What's the idea? The idea is that if you had a linear representation of this matroid, then points 1, 2, 3, 4, 5, 6, 7, 8, 9 would take physical positions in the projective plane, and therefore Pappus's theorem would apply, and 7, 8, and 9 would have to be collinear from this theorem of projective geometry. Okay? So whenever you try to represent this picture on the plane, 7, 8, 9 line up. Okay? But in this matroid, which is called the non-Pappus matroid, for obvious reasons, in this matrix 7 and 8 and 9 are independent. So this is a good example of, and this is a more conceptual example of how you actually build nonlinear matroids. Is basically you can kind of take a theorem from projective geometry and break it.
So in that picture, you can see one linear matroid and a whole bunch of
If you remove any point, you get a linear matroid. This is a minimal nonlinear matroid.
But you can remove any other line you want to.
You can remove any line and get.
Digest this, but can I ask a question back to this picture?
Mm-hmm.
The line there came from the actual physical line. The line 2, 4, 5, 3 came from that physical line. Line in the picture. Right?
The line 2, 4, 5, 3 came from, so it's a physical line here, which comes actually from a physical plane here.
So
It's the plane determined by 2, 4, 5, and 3.